Hello friends, in this video we're gonna discuss about Fermi-Dirac law of energy distribution in terms of Fermi energy, okay? And using the expression of Fermi-Dirac law of distribution, we are going to prove that average kinetic energy is equal to 3 by 5 times of EF. EF is the Fermi energy, okay? So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. The Fermi-Dirac law of energy distribution is given by this relation, okay? And these are the meaning of the terms used is in relation, okay? Now we are to prove that the average kinetic energy, or it can be written this way using this symbol as well, is 3 by 5 times of that Fermi energy, okay? We are to prove this one. So now let's start. Here you see, in terms of Fermi energy, the Fermi-Dirac distribution function, this is given by this relation I have already mentioned earlier in the for a previous slide, right? So at 0 Kelvin, that means at absolute 0, this function is equal to 1 for E less than EF, and it is 0 for E greater than EF, right? And density for free electron gas is given by, so we know that electrons, free electrons in a metal can be regarded as a free electron gas, okay? By this that is given by this expression, okay? Now you see, let me go to the next slide. The average kinetic energy can be can be calculated by dividing this integration from 0 to infinity g of E f of E into dE by integration g of E f of E dE, okay? At t equal to 0, as I have already mentioned, that here you see in this question that we have taken, prove that the at 0 Kelvin the average kinetic energy is 3 by 5 times of EF, that is Fermi energy. So that's why what we're gonna do, we are going to change this integrals, this limit up to EF, okay? And at 0 Kelvin, as we are taking the limit 0 to EF, so that means E less than EF, you can say for that case, as I have already given, that f of E is equal to, for E less than EF is 1, right? So that's why this f of E will be replaced by 1, okay, when the limit is changed to 0 to EF instead of infinity, okay? So hope you have understood this. So now let us evaluate these two integrals. Here we're going to put the expression of g, this one, okay? We are going to use this expression here in this equation here, okay? So, and first let me show you how to obtain this integral. So let me go to the next page. Here you can see integration E g e dE. So here this part is constant, and E into e to the power half, that's going to be e to the power 3 by 2. So here we have written 0 to integration 0 to EF e to the power 3 by 2 dF. So if you integrate this integration of using this x to the power n dx, that is x to the power n plus 1 by n plus 1, using this integration, we have got this. Actually we should get this result from this integration gives e to the power 5 by 2, and here 2 by 5. Actually we should we have got e to the power 5 by 2 by 5 by 2, right? So which becomes 2 by 5 times of this, right? Now we have taken the limit from 0 to EF. If you put this EF here, then you will get this one, then minus 0, so that remains 2 by 5 EF to the power 5 by 2. Hope you have understood this, right? Similarly, we have to evaluate this integral. Here you see this one. So now using these two results in this equation number 1 here and here, let's put these two equations, two results here. Putting these two results in equation number 1, we're gonna get this. Okay, we're gonna get this relation, right? Hope you have understood this. So here these two parts gone, so 2 cancels, so it becomes 3 by 5, and EF to the power 5 by 2 divided by EF to the power 5 by 3 by 2 means here 5 by 2 minus 3 by 2, and doing so we have got this relation. So hope you have understood this, right? So that's how we can prove this. Let me show you from the first page. So here is the first page, right? This is the second, and here is the third page. Okay, this one is the fourth page, and this is the last page, fifth page, right? So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.